So we're going to have very distinguished speakers from all around the world speak on the areas of their expertise. And our first speaker is going to be Professor Krishna Narayan. I'll let Bhagwat brief us.
Okay, so welcome everybody for this inaugural talk of the INFER seminar series. It's my distinct pleasure to introduce one of my professors, Professor Krishna Narayanan. So Professor Krishna Narayanan is the Sanchez Chair Professor in the Department of Electrical and Computer Engineering at Texas A&M University. And of course, I mean, his interests are broad and they sort of encompass the areas of coding theory, information theory, signal processing, and machine learning with particular applications to wireless communications. He's actually the winner of several awards, too numerous to list out one by one. But most recently, he won the 2025 Spark Best Paper Award and the 2022 Joint Communication Society and Information Theory Best Paper Award. He's an elected fellow of the IEEE, and he's widely regarded and recognized for his contributions to coding theory for both wireless communications and more recently data storage. So Professor Krishna is not only a stellar academic, which he obviously is, but he also recently co-founded a startup called Encando, which has developed an AI-enabled platform for teaching and learning. So on a personal note, I mean, I should say that I was extremely lucky to have, come in association with Professor Krishna during my PhD program. He was, as I mentioned, one of my professors. He taught me probabilistic graphical models. And what really struck me was his, ability to communicate, extremely complex ideas, distill them and communicate them in a very, very simple and lucid manner. That in some sense is also the theme of this seminar series, which is to sort of present cutting edge developments in sort of a tutorial style and make it accessible to starting graduate students. And so we could think of nobody better than Professor Krishna to sort of inaugurate this seminar series. So with that, let me thank Professor Krishna once again on behalf of all attendees for accepting our invitation to talk in the seminar series. And without further ado, I will yield the floor to Professor Narayanan. Thanks again, Professor Krishna.
Thank you, Bharadwaj. Thank you for that overly kind introduction. It's an absolute pleasure to give this talk. I always enjoy giving talks to audience in India, but particularly this format seems extremely interesting. So when Bharadwaj asked me to give a talk at this new seminar series, I was really quite excited to accept the invitation, and so here I am. First of all, I wish this seminar series success. So it seems like a very innovative format. I hope it really turns out to be something that's broadly useful for a lot of people. Having said that, so I'm going to talk about diffusion models. Diffusion models have been in the news a lot lately. They are a very interesting class of generative models. So I'm going to try to talk about what diffusion models are, and I'm going to try to get through the details of how to train one particular form of diffusion models. First of all, you may have already heard of diffusion models, particularly in the context of text-to-image generation. They became really popular when models like DALL-E, Midjourney, all these models started generating very high quality images from text prompts. So if you go to ChatGPT or Gemini today and try to generate an image based on a text prompt, the underlying model is really a diffusion model. You may have also seen many interesting image editing software, like people upload an image and ask somebody to replace a dog picture in the image with a cat picture or do various kinds of editings. Several of these editing software also are based on diffusion models. Not just in the image domain. Music generation, there are many models where you can ask a model to generate music in a particular style, and that also seems to be based on diffusion models. Video generation, you get the point. It's even beyond this. I'm particularly interested in wireless communications. It turns out that they are actually useful for some things in wireless communications as well. So I may not get a chance to talk a lot about it, but at least I will try to mention a few things. So first of all, let me set the stage by talking a little bit about what generative modeling is and why we should care about this. So the mathematical setup we have is this. So we have a vector x, which is a d-dimensional vector, And the general interest in the case when this random vector has a fairly complicated density function. So for example, we might think of X as a flattened image. We just take all the pixels in the image, we flatten it into a vector, and X might now be the vector of interest. The viewpoint we are going to take is that every image is a realization of this random vector, right? So if I think of it that way, clearly there is a lot of dependence between all the pixels. So each pixel is not independent of each other. So there is some underlying complicated structure that might define what a valid image or a commonly seen image is. And the setup is that we don't know this Q of X. Not only is it fairly complicated, we actually do not know this either. But what we do have is a data set with a bunch of samples drawn according to this distribution. So in the image case, it's very easy to collect billions of images on the internet and make a data set of images, right? So we really don't know what the underlying distribution is, but we can collect a big data set. And once we have this, we want to train some kind of a model to do two things. First thing is we want to generate more samples from the underlying distribution, new samples from the underlying distribution. That is going to be the bulk of what I'm going to talk about today. But sometimes we might also want to use this to solve inverse problems, meaning imagine I have some observation of X. So, and I'll give you a concrete example on the next slide. So maybe I get to observe X through some blurring or some kind of a process with noise, and I want to try to reconstruct X from Y. And quite often, these kinds of problems in engineering are ill-posed. There are many possible X's that can explain the same Y that we observe. And often what we want to do is to impose a certain prior knowledge that we have about X to be able to solve this problem in a meaningful sense. But if that prior is very complicated, we can use a diffusion model that can learn this prior and help with the inverse problem. Okay. So here is an example of generating new images. So this is a data set that you collect, a bunch of images, you train a model, and you can see here are the new generated images from the data set. I mean, you can see these generated images are fairly realistic. I mean, it's not perfect, so you can see there are some, you can think of artifacts here and there, but in general, they are fairly good, right? So here is an example of some kinds of inverse problems that you might want to solve. So here is, in this column, you can see the ground truth. So these are the real images. And for example, we can have what we call as box in painting. So maybe you lost some part of the image. So you have an observation of the image, but you have lost some part of the image, and you want to reconstruct what was lost. So clearly, when you try to do the reconstruction, you want to make sure that you use the information in your observation, but also something in the prior to be able to interpolate between the things that you have seen, right? So I've shown you some examples of things that interpolate better, or not all of them are more or less diffusion model based. So you can have blurring, for example, here, this is like you have a camera that was shaken during the picture. All these kinds of different things. These are possible examples of inverse problems. In wireless communications, what you might have is an example of a noisy channel estimate. You might transmit pilots. You get to observe what you receive at the, so for example, in wireless, we might get to observe H plus N. So H may be a MIMO channel matrix. And what you might want to do is to denoise, or you want to make a better estimate of H from Y. And in this case, you want to take advantage of prior information that you know about H. Quite often, we use simple stylized models for H, But in reality, measurements may tell you that these are not really truly reflective of what really happens in the channel. So it's better for you to collect a data set and try to learn an underlying distribution and try to denoise H based on that observation. So these are all just some examples. Now, images are nice, visually they are very nice to see and things like this. But if you want to really understand something in a 1 hour lecture, I think these are too high dimensional for us to really get some insight into this. So what I'm going to do is I'm going to work with a simpler example, an example in 2 dimensions, so that we can concretize a lot of things that I'm going to talk about. So here is an example of a 2 dimensional random vector. And what I've showed on the left-hand side, so this random vector has a mixture Gaussian distribution. So there are 3 modes, and for each mode, there is a mean, you can see here, here, or here. And then there are 3 different covariance matrices for each mean. So when you take a mixture of all of them, the probability density function is shown as a heat map on the left. So bright regions means there are higher, the density function is higher. And you can see that it's a mixture Gaussian, but if you just look at it as a distribution, it's a pretty complicated distribution, right? So it has some very weird regions where you have large values for the probability density function. And so here is an example of a data set that might be drawn from this distribution. If I just randomly generate 200 samples from this, you might get some kind of a distribution with this. So we might start with this data set, and the goal is to learn a model that will produce more samples from the underlying distribution. Bharadwaj, I'm happy to stop and answer any questions at any time if people have. I don't know what the format of the seminar you envision is, but I'm very open to answering questions as we go through.
Sounds good. Yeah. So if we have questions here, maybe you can just raise your hands and then we can take it during the lectures.
Okay. Now, there have been a large, so diffusion models have been very popular for this kind of generation, but there is a very large amount of work in general on generative modeling. And diffusion models themselves can be traced back to developments in what are called variational autoencoders, normalizing flows, or generative adversarial networks. There is a lot of history behind this. And I will not be able to go through all of this history. I will not be able to place particularly what I'm going to do within the context of all this. I think that is a little bit ambitious for a 1 hour lecture. But what I will do is this. There are 3 popular flavors of diffusion models. We will focus on one of them called denoising diffusion probabilistic models. And what I will try to do is to help you understand how these models are trained. In particular, the one takeaway from this lecture should be to understand what I'm going to define as a denoising process, how to train a model to do the denoising, and how to sample new samples from the underlying distribution. Really, if you're a student, you want to learn this, you should be able to write your own code to train a neural network. That should be your goal, to make sure that you actually understand what happens. I have a Python notebook, which I will do a little bit demo towards the end of this, and I will make the notebook available as well. The notebook has some typical features for generating the data set, so on and so forth. If you can write your own training part of the program, then I think you have understood what you need to. So that's there are many nice tutorials on diffusion models, particularly on the web as well. I have particularly drawn from these 6 papers. The book by Bishop and Bishop is I like it a lot. And then there is this paper, which also I've drawn heavily from to make this tutorial. So having said that, okay, one last thing before we get into the details, a little bit about notation. So I'm going to use capital letters to denote random vectors. And I'm going to use lowercase letters to denote realizations. Typically, boldface capitals are used for matrices. Unfortunately, we're not going to use any. In this talk, they're actually going to refer to random vectors. Okay. So they are not matrices, but they are really vectors. All right. With that, let's try to get into some of the details. So there are really two processes that we need to understand in trying to understand what these diffusion models are. There is what is called as a forward process. So in a forward process, you can think of it as taking an image from your data set and progressively adding noise to the image over many steps, progressively noising the image to end up at the end of the process with an image that's almost entirely noisy. By the way, when I keep saying image, but of course, you can think of it as any vector, right? You start with a vector, you're going to add Gaussian noise to this vector, and you're at the end of the process, you kind of are going to lose the entire signal. You're going to be dominated entirely by noise. So this is called as a noising process, or this is called as the forward process. And the goal in a diffusion model is to try to learn a reverse process based on this, which at every step tries to form the best estimate of the previous step based on the noisy image that we have. There is a little bit of a misleading nomenclature in the literature where people think of it as undoing or reversing the forward process. This is not entirely accurate in the sense we're not going to do anything that will completely remove the noise. But what we are going to learn at every stage is to make the best estimate or learn a conditional mean at every step for the previous step given the current step. And during the generation, what we are going to do is this. We're going to start with a new noise sample. And then we're going to run this process in reverse and show that this is going to generate a new sample from the original distribution. There are a few things I want to emphasize very clearly. I intentionally want to make sure that the reverse process, in at least the form of diffusion model that I'm going to talk about today, is not going to produce exactly the same image that you start with. The forward process is something that's used only in the training. And in the reverse process, you're going to generate a new image. So you see that this dog image is very different from this dog image, although both of them are dogs. I think a very good physical analogy is to think of, if you take ice in a box and you heat it, the ice will melt. If you can refreeze the ice, if you freeze the ice, you will get another ice block back. But if you really look at the molecules in the ice, they are not going to be exactly the same as what you started with, right? So this is the process of noising and reversing the process where you get another realization from the same distribution, but not exactly the same realization itself. Okay. All right. And we are going to think of it in terms of a graph of random vectors. We call it as a probabilistic graphical model. So we're going to think of X as our original sample. This is from the data set. And then the Z's are called latent variables, but essentially these are just noisy versions of X as far as this talk is concerned. So we have a total of T capital steps. Oops. Just, oops. Yeah, so we have a total of T capital steps. And what we are going to do is this. So let me actually go to the forward model. So I'm going to get specific here. So the way we get Z1 from X is I'm going to take X, multiply it by a number less than 1 minus beta 1 times X, plus square root of beta 1 times a Gaussian random variable with zero mean and unit variance. So we are scaling back X a little bit, and we are adding a little bit of Gaussian noise to it. So that's a noisy version of X, right? Now I continue to do the same thing from Z1, I get Z2. But now I'm going to call my constant in front of Z1 as square root of 1 minus beta 2 times Z1 plus square root of beta 2 times beta 2. So you can see that I can compose these two steps together, and we can think of Z2 as the product of these two, which is square root of 1 minus beta 1 times 1 minus beta 2 times X, plus there is some equivalent noise. Right? Notice that these noises are completely independent of X, so I can put everything together into equivalent noise, and the variance of this noise, will compute what it is, but you can say, see, I can think of it as an equivalent Gaussian noise. Okay. Now I want to step back to this graphical model, and we want to try to understand some of these conditional distributions. So first of all, notice that at any point, because of the way that I'm constructing my ZT from ZT minus 1, by always taking ZT minus 1, scaling it back a little bit and adding additive Gaussian noise, the conditional density of ZT given ZT minus 1, this is always Gaussian. Right? Because what I did was to literally just add Gaussian noise. However, the density of ZT minus 1 given ZT is not Gaussian in general. Why is that? Well, the prior on ZT minus 1 may not be Gaussian. Remember, X comes from some complicated distribution. ZT minus 1 was obtained by taking X and then adding some noise to it. So I start with some complicated distribution, I add some Gaussian noise to it. I'm not going to get anything that's necessarily Gaussian, right? So the prior on ZT minus 1 is not Gaussian, and so conditioned on ZT minus 1 is not Gaussian in general. So computing this distribution is going to be a bulk of what we are going to look at in the lecture, but it's important to realize that it's not Gaussian. So what we are going to do is this. We are going to somehow approximate this distribution by using a neural network. In particular, the plan is to show that in some cases, this can be approximated as a Gaussian. And that approximation is exact in certain limit. And since this is Gaussian, I can learn the mean and variance of this Gaussian by using a neural network. So this is going to be our plan. Our plan is to somehow learn to generate samples from ZT minus 1 given ZT. So this is the reverse process. Okay. Okay, now let's go back to the math here. Now, notice that we see that if I continue this Z1, Z2, this chain of random vectors, we're going to get ZT, which can be written in two equivalent ways. So one way to write ZT is to think of it as a small perturbation from ZT minus 1. So it's square root of 1 minus beta t times ZT minus 1 plus square root of beta t times a Gaussian random vector eta t. It can also be written in terms of x, right? ZT is square root of alpha t times x plus square root of 1 minus alpha t times epsilon. Now, when I do this, clearly there is a relationship between alpha and beta. And you can see that alpha t is simply the product of all the 1 minus betas starting from the beginning. So here you can see there was a product of two betas, 1 minus betas. We're just going to have T of them if I go further down. Okay. So picking these betas are somewhat important. How you pick them is important. And in general, what we are going to do is to pick betas to be small. They are linearly increasing with time from something really small, like 0.0001 to something like 0.02. In this case, so these betas are really very small. But these alphas, which are all product of 1 minus betas, you see that the alpha is going to start at 1, but over time, it's going to decay and go to 0. And of course, 1 minus alpha does the opposite. So the way this is going to happen is, so we are going to take many discrete steps over time, right? So for example, a few hundred steps or up to 1,000 steps in T. There is a beta for every one of these values, and there is an alpha corresponding to every one of them. And what I want you to note is this. If you look at this expression between ZT and X, you can kind of think of a signal to noise ratio for this, right? So the power in the signal is alpha T, whereas the power in the noise is 1 minus alpha. The variance of the noise is 1 minus alpha T. So if you think about the signal to noise ratio, as T increases, the signal to noise ratio is becoming really, really small, right? So you've kind of noised your original vector a lot. So keep in mind that in this process, this SNR is becoming really, really small. Towards the end, you have very low SNR. Okay, this is something I'll come back and we'll talk about. Okay, so I want to stop here and just make sure that so far everything is okay, because we're going to get into the important parts of how to compute the reverse conditionals here. So I hope the setup is clear. Okay, I see a hand raised.
We have a question.
Yeah.
Sir, just one clarification needed in the reverse process. I mean, should we take always a different noise sample or same noise sample? If we take, then what will happen?
Okay.
The reverse
So
process.
yeah, very good question. So I'm going to talk a little more about the reverse process. The short answer is we are going to take a different noise sample every time. So if you end up taking the same noise sample, this is not going to give you good images because you will not be sampling from the actual distributions that you need to sample from. So what we call the version I'm going to describe is what is called a stochastic sampling version. We'll get to it. Please be a bit patient. We'll get to it. But there are versions where you can do a deterministic sampling, but they are a little bit different. In this setup, if you just fix the sample on the reverse to be exactly the same, you will not get good. You will not be sampling from the true distribution X.
So, like a follow-up, can we get back the same original sample if we have taken the same noise sample in the reverse?
No. No.
Okay, sir. Yes.
Yeah, we will. I think that's really important to understand. So, in the setup, you have to think of this as a mapping from the distribution of X to a Gaussian distribution, not really at a realizational level. Like you're not really trying to say that I'm going to map every X to a particular noise realization. Not in the version I'm talking about. In this idea of what is called as denoising diffusion probabilistic models, this doesn't happen. There are other models where you will be able to find a deterministic map. But in this, it's only a map from the distribution on X to a Gaussian distribution. Okay. Very good. Okay. So now we want to somehow try to compute the reverse. And like I said, the whole idea is this. The idea is that we will draw a sample for ZT, and then at every stage compute Q of ZT minus 1 given ZT.
So, Professor
Sample
Krishna,
from Q of...
there is a question on the chat.
Oh,
Are you
okay.
able to see that?
Let me see. Give me 1 minute. Oops.
Shall I read it out?
Yeah,
So the
please.
question is, yeah, so what's the idea behind doing many steps in the forward process? And can central limit theorem be invoked to say that the distribution is Gaussian? Since
So,
you said that we want to approximate it as a Gaussian in the limit.
okay, so let's be very clear. ZT is Gaussian. You are adding a large number of noise samples to get to ZT. In fact, we don't even need central limit theorem to get to ZT. Every noise you are adding is really Gaussian noise. So ZT is indeed Gaussian. The statement I made about something not being Gaussian are the conditional distribution. So you cannot really say that QZT minus 1 given ZT is Gaussian, right? Not unless you make some assumptions, which is what I'm going to talk about now. So you have to be careful about what you want to be Gaussian and what. So X is not Gaussian, right? That first we have to make that very clear. Our interest is really in the case when X has some very complicated distribution. So X is not Gaussian. So everything that follows is really not Gaussian unless you go to the right end, unless you take the limit of this. Okay. All right. So now I want to make a case that in some cases we can approximate Q of ZT minus 1 by ZT as Gaussian. Now there is a formal proof for this. I'm not going to do the proof. I'm going to give you a visual intuition for why you can make the assumption that this is Gaussian when beta is really small. And when you cannot make the assumption, and why you cannot make this assumption that it's Gaussian if beta is large. So let's first consider the large beta case. Okay. So what is large beta? So first of all, let's think about this a little more. So if I want to compute
There's
Q
one
of
more
Z,
question.
yeah.
Sorry to interrupt, but what does the axis represent here, sir? And what does this like mean represent in the four plots?
Okay, yeah, I will explain the plots. Just give me 1 minute. I will explain the plots. So I want to compute Q of ZT minus 1 given ZT. All right, I'm going to use Bayes' theorem, write it as ZT given ZT minus 1 times the prior on ZT minus 1, and then the denominator is just a normalizing constant. Okay, so I've shown 4 pictures here. So this picture shows you a plot of Q of ZT given ZT minus 1. So the first part here. When beta is reasonably large, well, what's the effect of beta being reasonably large? That means the variance of this Gaussian distribution is large. Its mean is ZT minus 1, and the variance is reasonably large. So I've drawn it as a, rather broad Gaussian. And this is the case Q of ZT given ZT minus 1 when the variance is small, so it's clearly peaked. Okay. Now, this plot, let's first look at the red curve on that plot. So the red curve on the plot is the prior density for ZT minus 1. So I've chosen intentionally something that is not Gaussian. So you can see there are, it seems like it's a mixture Gaussian, right? So there are three peaks in that distribution. So the red curve there is the prior on ZT minus 1. So the blue curve is the posterior. We're going to compute Q of ZT minus 1 given ZT. And imagine I want to compute the posterior at this point. So I pick a value, I have to compute q of zt minus 1 given zt for all values of z, right? Q of zt minus 1 evaluated at various values zt minus 1 can take. And let me fix this particular value here. How do I compute this? Well, what I need to do is I have to take the value of the prior on the red curve. I have to compute the density. So imagine that if my zt is here, right? We are conditioning on zt. So I have to evaluate the Gaussian density of zt given zt minus 1 with the mean being zt minus 1. So I take this value, I multiply by this value, right? I need to multiply these two together, and the point I want to make is this. If beta is very large, this is not really small. So what I end up getting is a little bit of a reduction from this red curve, but you still see a pronounced peak in the blue curve. So the blue is the posterior, and you can see that it doesn't really look Gaussian. Now, in contrast, think about the case when beta becomes really small. So what do I need to do? In this case, I have to take the density of zt given zt minus 1 at this point, and I have to multiply it by the prior here if I want to compute the density at this point. But now you see that this is really, really small. So this thing gets all squished all the way down here. So essentially, these two peaks kind of go away. The only thing that happens is if you were to center this distribution somewhere here, so this is the only peak that remains if beta is really small. Okay. So the bottom line is that if beta is small, then you can make the approximation that the posterior is Gaussian. Now, this can be formalized. It can be proven that in the limit as beta goes to 0, indeed this is Gaussian, which means if you look at the KL distance between a Gaussian and the true distribution, that goes to 0 fast enough that so even though you take t steps, in the end, this approximation does not really affect you. Okay. So this is an important thing. So then our whole process is going to work like this. We're going to draw a sample. So zt is Gaussian. So you're going to draw a sample here. And then you're going to do the reverse process. So at every stage, what you are going to do is this. You're going to pass your zt minus zt through a neural network. What the neural network is going to do is this. It is going to predict the mean of zt minus 1 given zt. And we will see that the variance is actually completely independent of zt. So we don't even need a neural network to predict it. The bottom line is we are going to compute the mean and we are going to compute the variance. And most importantly, we are going to sample from this distribution. We're going to pick a Gaussian random variable with this mean and this variance. And we're going to set our zt minus 1 to be that. And then we keep going forward, going backwards. And then you generate a sample from X, and it actually you have generated from the true distribution. So going back to the very first question, this process is important. This sampling is independent from time to time. So I'm not going to draw the same noise at every one of these samples. So that is really important. Okay. Now, as I have pointed out here, it looks like what I need is a neural network to learn the mean at every given time. Right? So in principle, for every t, I learn a different neural network. But that's clearly not practical. You cannot learn a different neural network for every t. So what we do in practice is you add t as an input to your neural network. So your neural network is going to take two inputs, t and zt. And it's going to produce a mean as the output. And we'll see that the variance does not depend on zt. So you have a mean, you have a variance, you're going to sample from that distribution. You're going to keep going backwards. Okay. Now, the structure of the neural network that you put actually does matter It depends on the domain from which you want to sample. So if you're doing images, you typically put UNets. If you're doing simple two-dimensional examples, fully connected neural networks may be enough. If you're doing channel estimation, CNNs work well. So there is some, you need to be clever about the structure of the neural network that you put on the inside this, but we won't talk too much about this. Okay. In the next 30 minutes or so, I'm going to try to show how to actually do the training. Okay. Now, in the literature, if you go read papers on diffusion models, there are different ways in which people talk about this. They typically use what is called as evidence lower bound and many things which for a first attempt seem rather difficult to grab. I think it's possible to avoid all of this and do something fairly simple based only on estimation. In the spirit of this seminar series being a INFER where the E is for estimation, I thought maybe a good first lecture to talk about just estimation principles to see how to design this the neural network. I'm going to start with very simple results in estimation. So let's say that we have three random variables, X, epsilon, and Z. Okay, so I have X, I have epsilon, Z. This is pretty much the same model that we have been interested in, where Z is just some square root of alpha times X plus 1 minus square root of alpha times epsilon. And let's say I want to make an estimate of X from Z. We want to estimate X from Z. There are many estimates you can make of X from Z, but what we know is that of all those functions that you can use, the conditional mean minimizes the mean squared error. So if I can compute the conditional mean of X given Z, then I will end up minimizing the mean squared error, which is defined as the expectation over the joint distribution of X and Z of X minus your estimate, which is f of Z. Right? Okay, so this is fairly classic in signal processing. There is something really interesting that people seem to do in machine learning, which is to say, look, if I want to estimate X from Z, I can also estimate epsilon from Z and then subtract 1 minus square root of 1 minus alpha times epsilon. This is not something that is fairly standard in signal processing, but there is a good reason to think about it for this particular problem. But for a minute, let's just think about estimating epsilon from Z. I mean, Z is something that's correlated with epsilon, right? So if I want to minimize my mean squared error in estimating epsilon from Z, then the function, the estimate of epsilon that minimizes that is simply the conditional mean estimate of epsilon given Z, right? Now, if I can get that estimate, then of course, by algebra, what I do is I subtract, I can compute the expected value of X given Z by taking Z subtracting square root of 1 minus alpha times the conditional mean and dividing by square root of alpha. So conceptually, there is no difference if you want to estimate the conditional mean of X from Z or the conditional mean of epsilon from Z, and you can get one from the other, right? But the thing is, these estimators have fairly complicated, they are complicated functions. It's not easy to find this function. So our approach is going to be use a neural network to learn the expected value of epsilon given Z, or equivalently G of Z. We'll parameterize this by a neural network, and I will try to learn this. Okay. Now, this is kind of an important slide in terms of how to do this in a data-driven way. So let's think about just these three random variables. Forget diffusion and all this for a minute, right? I have X, I have epsilon, I have Z. I want to make an estimate of epsilon from Z. How do I train a neural network to be able to do this? Well, The one way to do this is to do the following. Draw samples from X and epsilon. In our case, X and epsilon are completely independent of each other. So draw a sample for X, draw an independent Gaussian random variable epsilon, and do this B times. So you can make a data set. So each point in the data set has a X comma epsilon pair. From X and epsilon, I can form Z, right? So I can form triplets X epsilon Z in my data set. I feed Z into a neural network, and I try to minimize the mean squared error between the epsilon in my data set and the output of the neural network, which is G of Z. I simply train the neural network, right? Minimize the mean squared error between epsilon and Z. If my training is good, my neural network is going to learn the conditional mean, because the conditional mean is the one that minimizes the mean squared error. So at the end of the day, it's a really, really simple idea, right? If you want to ever estimate a conditional mean, set up an optimization problem where you minimize a mean squared error, and you naturally are going to learn the conditional mean in this process. And the most important thing is, all you require here is a data set with X epsilon Z triplets. If I can create X epsilon Z triplets, then I can just do this training and I can learn a function that will give the conditional mean of epsilon given Z. And of course, if I get epsilon given Z, I can get X given Z. Does that make sense? Okay. Now, how do we take this and what do we do with the diffusion model? At first, it seems like we have really solved the problem, right? So what did we say we really wanted to do? Our goal was to compute the conditional mean of ZT minus 1 given ZT. Now, I know that I have a model between ZT minus 1 and ZT, right? I know that ZT is simply 1 minus a square root of 1 minus beta t times ZT minus 1 plus square root of beta t times eta t. Now, what I can do is I can take one sample from my data set X, I can add noise, I can create a sample for ZT minus 1, add another Gaussian noise sample, and I can create ZT. So I can create triplets ZT minus 1, eta t, ZT, and I can create a data set with this. I pass my ZT to my neural network. I ask it to predict either eta t or I ask it to predict ZT minus 1, minimize the mean squared error. I will be able to learn the conditional mean of ZT minus 1 given ZT. And we were done, right? Unfortunately, this doesn't work well in practice unless you have a very, very large number of samples. So it turns out that the variance of this estimator is a bit high, and it can be reduced by doing something slightly more complicated. And that's what but in principle, this is what it is, right? In principle, this is what you're going to do. But we're going to take a slightly harder way to do this, which is to not directly compute the expected value of ZT minus 1 given ZT, but we are going to go through X. Yeah, the main problem is that the estimator has high variance if you do this. So to decrease the variance, we are going to do this in 2 steps. Again, we should keep in mind that our goal is to compute this.
Krishna, quick question.
Yeah.
So everything you've said works even if that, this conditional distribution of ZT minus 1 given ZT is not Gaussian, right?
Absolutely. To compute the expected value of ZT minus 1 given ZT, you are absolutely right. I will end up estimating that correctly. However, if I want to sample from ZT minus 1 given ZT, I ultimately want to draw a sample from ZT minus 1 given ZT, right? Now
Right.
it's not enough for me to know the conditional mean of ZT minus 1 given ZT. I need to know the full distribution of ZT minus 1 given ZT. So I need to make some assumption, or I need to argue that this is actually Gaussian.
So then you start with X and you can form ZT minus 1, right?
Right.
So is that not a way of sampling from ZT from the distribution?
No, you want to generate new samples. Remember, X are your data from the data set.
I
So
see.
when you do the reverse sampling, you don't want to use anything from X. You want to start from ZT, a new noise sample, right?
I see. I see. So when you're training the neural network, it's you're not using the X.
So when you are training, you are using it. When you are training it,
Oh,
you
right,
can
right.
create ZT minus 1 from X. That's perfectly fine.
Got it. Got it. Got it.
But when you do the reverse, you don't want to use anything from X. You only want to use the conditional mean of ZT minus 1 given ZT that you have learned in the forward process.
Got it. Okay. Okay. So in the reverse process is where you sort of use the fact that it's sort of Gaussian in the limit and so
Yes.
on. Okay.
Yeah. But you are absolutely correct that the difficulty is not in actually computing there are two important pieces. That's why in the beginning, so there is a denoising step, which means computing the conditional mean, and there is a sampling step, which means I need to draw a sample for ZT minus 1 from the distribution of ZT minus 1 given ZT. And for the denoising step, for the conditional mean, we are using a neural network to estimate that conditional mean. For the sampling, we are making a Gaussian assumption to sample from the Gaussian distribution. But this assumption, like I said, it's provably correct.
Got it. Got it.
Professor Krishna, I had one other question.
Yeah. Yeah.
So at the end of the day, our goal is to estimate X, right? So
No. Our goal is not to estimate X. Our goal is to generate a new sample from the underlying distribution.
Right.
Because see, so if you think about, there is no X to really, okay, if you're thinking about solving an inverse problem, there is a goal of estimating X. But so far, most of what I've talked about is about generating new samples for X.
No, I was thinking, I mean, we have, so one way of doing the reverse process is by generating these distributions P, ZT minus 1 given ZT and so on.
Right.
The other way is to actually look at each ZT possibly as a noisy version of X itself. And what you're trying to do is to kind of, I was thinking if the problem were to estimate X, then the problem is to just put together these different noisy samples to just get a reliable estimate of X.
Yeah. So, okay, first of all, that is a different problem, right? So, that's not the problem we are at least at this point interested in. You see, because even if you want to denoise ZT to get X, you need a good way to understand the prior distribution of X. Right? So yeah, in that problem, you are right. So if you give me an observation ZT, which is a noisy version of X, then all you're really trying to do is to estimate the conditional mean of X given ZT.
Correct, yes.
Yeah.
Given all the
I would agree with that.
Yeah.
I would agree with that. But even for that, you have to learn this process, right? And it actually turns out that it's better for you to take many small steps rather than try to learn this directly.
Cool. Thanks.
Yeah.
Any other questions?
Shall I go on?
Krishna, one question from me. This is Andrew.
Hey, Andrew. Yes.
So you mentioned some high variance somewhere. Why is that variance high? Is there a quick way to see it?
Yeah, this is actually a really interesting thing. I don't know if there is a quick way to see it, but the intuition for this is the following. If you think about, so there are two options, right? So you can either estimate eta t from ZT, or you can try to estimate epsilon t from ZT.
Okay.
In that
Oh,
process,
okay.
you will end up getting a conditional mean of x, and from there you can get the conditional mean of zt minus 1 given
Okay.
x.
Okay.
So it turns out if you try to estimate epsilon t, notice that epsilon t is actually the sum of many, many etas, right? Eta is
Okay.
the one-step noise.
Okay.
Epsilon is the cumulative noise.
Okay. Okay.
So it turns out your estimator actually has some averaging. So epsilon is like the average of many etas. So it turns out you get better averaging and some variance reduction in the finite sample size. But
Okay.
you are correct that, if you have asymptotically large number of sample sizes, there is no difference between these things. It's really a finite sample difference.
Okay. Thanks. Thanks.
Yeah. So what we are going to do is to do this in 2 steps. The first step we are going to use is to compute the expected value of zt minus 1 given zt and x. Right? The conditioning on x is not what we really care about, but we are going to put the conditioning and estimate that mean first. And then average over x conditioned on zt to be able to get the iterated expectation of zt minus 1 given zt. So let's see how to compute both of these in the next few slides. So first thing, computing expected value of zt minus 1 given both zt and x. Okay. So notice here we have 3 random variables x, zt minus 1 and zt. Now conditioned on x, zt minus 1 is clearly Gaussian. Right? So maybe we'll do this. So what do we want to compute? So imagine I want to compute. Actually, before I do this, so I'm going to show that conditioned on zt and x, zt minus 1 is Gaussian. Now, if I drop the x, that is when you get in, things are not in general Gaussian, but when small beta limit, it is Gaussian. But regardless of large beta, small beta, if I condition on both x and zt minus 1 is Gaussian. And to see that, you can see that I can expand this as q of x times q of zt minus 1 given x and zt given zt minus 1 and x. And then of course, oops. And then I have some denominator. Right? I mean, the only terms that depend on zt minus 1 are these 2 terms. So this is clearly Gaussian. Right? zt minus 1 given x. But notice that q of zt given zt minus 1 and x conditioned on zt minus 1, x doesn't have anything to do with zt. Right? There is a Markov chain between x, zt minus 1 and zt. So this is simply zt given zt minus 1. This is also Gaussian with the mean being zt minus 1 in zt. But if you condition on both x and zt, it turns out it's a product of 2 Gaussians, which after a little bit of algebra, you can see it is actually Gaussian. I think I'm already nearly kind of at the 1 hour limit. I'll finish in the next 15 minutes. So I think I'm going to leave the rest of the proof for people to work, but this is indeed true that zt minus 1 condition on x and zt is Gaussian. And if you actually do the algebra, what it will turn out to is this. So we'll call that mean as x comma zt. So it's going to be some function of x and zt, right? Because it's the mean of zt minus 1 condition on x and zt. Turns out it's just some linear combination of x and zt. There are some coefficients in the linear combination. And then there is the variance of zt minus 1 given x and zt. And when you compute the variance turns out to be completely independent of x and zt. So notice that this is independent. Okay, and that's kind of understandable because imagine this, right? So you have these three random variables, but I give you x and zt. Now, the variance in your estimate of zt minus 1 given x and zt is got to depend only on the quality of these channels, right? And that depends only on the variance of those channels. It doesn't really depend on x and z itself. Okay? But the mean, on the other hand, of course, depends on x and zt. So there is only one more step before we conclude. So far, what have we done? We have computed zt minus 1 conditioned on zt and x. And now what I need to do is take that and average over x given zt. So this is what I wanted. This was our goal. Our goal was to compute expected value of zt minus 1 given zt. So I take the expression that I had on the last slide. So it is this expression. And then I'm going to take the expected value of that with respect to x. So what do I get when I move this? Well, I'm going to get expected value of x given zt. We're going to get expected value of zt given zt, which is just zt. Okay, so far at this stage, we have conditional mean of x given zt and then zt. Zt is given to us, right? We are going to feed that into a neural network. Now, I want to do noise prediction instead of signal prediction, and I'll tell you why in just a minute. I'm going to replace this expected value of x given zt by expected value of epsilon given zt. You remember we talked about noise prediction and how I can go back and forth between the conditional mean of x and the conditional mean of epsilon. So I'm going to replace x given zt by the conditional mean of epsilon given zt. Just plug it back into this expression. Notice that this has a zt, there is another zt here. We can put both of these two things together. Ultimately, we get something like this. The conditional mean depends on zt through one term, and it depends on the conditional mean of epsilon t given zt through another term. There are some coefficients in front. Those depends on the alphas and the betas, but otherwise this is simple a linear combination of these two. So what we are going to do is to use a neural network to learn this at every stage. I think this is the important thing. So we are going to use a neural network to learn the conditional mean of epsilon given z for every t. So I'm going to use t as an input to my neural network. So I'm going to learn a function z of zt parameterized by w. And it actually turns out, if I go back further, look at the variance. So this variance can be very well approximated by beta t because these two are fairly close to each other. So we will simply use the fact that sigma squared at every step is just beta t at that stage. So notice, remember, beta is really small. So okay. Now the question is, why do we want to predict noise instead of directly predict the signal, right? Why not just directly compute, use a neural network to estimate expected value of x given zt? Remember, I told you early on that as t increases, your SNR is becoming really, really small. So when you train your neural network, if you try to predict x from zt during the early parts of the reverse process, which is when t is very large, your signal to noise ratio is extremely bad. So it turns out it's much better for you to try to learn epsilon rather than learn x, or it's better to learn the conditional mean of epsilon t given zt rather than the conditional mean of x given zt. Of course, as your t becomes smaller, you're going to have the opposite problem, but in general, this seems to be a more stable way to train things. And also, there is a natural scaling in our thing where, epsilon always has unit variance, right? So we are always trying to predict a unit variance quantity. X, on the other hand, you don't have full control over this, even though you will normalize your data set, so on and so forth. But the most important reason is that in the early part of the training, your SNR is so bad that it turns out to be more stable to try to predict the noise, and from that get to the signal than to directly predict the signal. Okay, that's it. In the next 5 minutes, I'm going to put it all together and then say, okay, what is our training procedure? So this is our training procedure. You are given a data set. Data set has many XN samples. You are going to pick a noise schedule. You are going to pick betas, and from the betas, you are going to get your alphas. You are going to train to get the weights of a neural network. What are we going to do? We are going to take a mini batch, X1 through XB from the data set. And what I'm going to do is this. We're going to randomly sample time instants from 1 to t. Remember, we said we want to learn a neural network that works for all time, right? So I randomly pick b time instants. For each time instant, I create a Gaussian noise realization, epsilon. So now I have x, I have t, I have epsilon. So I can compute zt. So this is zt. I feed zt, I feed t into my neural network. I minimize the mean squared error between epsilon and t. And what would it do in that process? You will end up learning the conditional mean of zt minus 1. You will end up learning the conditional mean of epsilon t given zt. But we know with this, we can convert that into an expected value of zt minus 1 given zt. So this is how we do the training. Okay. Now, once I have done this, what do I do for the sampling? Well, I have my trained network. I pick the same noise schedule. We first pick a Gaussian random vector for zt. And then the noise schedule also fixes your alphas. So what do? I take my zt, I add t, pass that to a neural network. Neural network would produce the expected value of epsilon t given zt. I convert that. So this whole thing, this whole expression in the end is just expected value of zt minus 1 given zt. And this is the most important step in the sampling. So this is my mean. And I've made an assumption that my distribution is Gaussian. And I showed you that the variance is beta. So what I'm going to do is I'm going to draw a new sample for zt minus 1 with the mean being what comes out of my neural network. That's my mean. The variance is going to be beta t. So I just draw a unit variance random number and then scale that by square root of beta t. Now I get my zt minus 1. We just iterate. Again, going back to the very first question, this epsilon is different for different steps. And I'll show you one more graphic, which is really nice in this. That's it. We just iterate this process, and this is just the last step. So I want to stop here and ask you, because these two are the most important things. This is what I want to be the takeaway from this lecture, is to be able to fully train your network. So you start with X, you randomly pick some time instance, you draw samples for epsilon, create your Z according to 5, according to line number 5, right? Feed that into a neural network, make it minimize the mean squared error between epsilon I and Z, and that gives you your conditional mean of epsilon given ZT. Convert that to an expected value of ZT minus 1 given ZT. and then do the reverse sampling. Okay. So I'll show you some nice picture. There is a very nice connection to score function. So Bharadwaj, how much time do I have?
I guess you can go for another 5-10 minutes.
Okay. So maybe then I will show you something and then I'll come back to it. So again, to reinforce that answer to the last question. So this is actually the process. So in this example, this is a Gaussian mixture with 2 Gaussians instead of 3 that I showed you before. So notice that if I start in the middle, so let's say I draw a random number for ZT. What is shown here are 3 trajectories. I've trained my neural network, it's exactly the same, but I start from ZT and then run the reverse sampling process. Because I'm drawing different noise realizations at each step, you can see what's happening at every step is that, I'm taking a step, I'm going from ZT to expected value of ZT minus 1 given ZT, that becomes the mean. And then there is a little Gaussian random variable that I add on top of that, right? So you can see that this path wiggles around all the way. But even if you start exactly in the same point, you can end up in completely different regions because you are taking many, many, many small steps. This is really diffusing over those many small steps. Okay, so even if you start in exactly the same ZT, you can end up completely in different points. Now, I want to show you a very nice connection to another thing in estimation theory. So the way I derived this is only one way to get to the derivation. There is another very common way to get to this, which is through what is called as the score function. So imagine that we have 3 random variables, x, epsilon, and zt. Right? Now, in general, x is not Gaussian, right? So it's not, like I said, it's not easy to make an estimate of x from z. However, if you only want the conditional mean of x given zt, it turns out there is a very nice formula that tells you how to get the conditional mean of x from zt, which is called as Tweedy's formula. So Tweedy's formula essentially says the following. It says you can think of your expected value of x given zt as kind of a correction to zt. So you can take zt and you can add square root of 1 minus alpha t times the gradient of the log of f of zt. Now, regardless of the distribution of x, this is going to give you the conditional mean of x given zt. So in statistics, this is of course called, this is a very well-known quantity. This is called the score function. In fact, it's called the Stein's score function. Okay. Now, notice this. We didn't really use this property, right? But what we could have done is this. We could have done is to say, hey, look, I really wanted to compute expected value of x given zt, right? But remember, in my 2-step process, my first step was to, no, actually, sorry. If I compute my expected value of x given zt, I can convert this to an expected value of zt minus 1 given zt. So what I'm really trying to do is we are trying to learn this function. I mean, it's easy to write this function, but it's not actually easy to get this function, right? Because the real problem is that zt does not have a simple distribution. X does not have a simple distribution. So zt does not really have a simple distribution. If you could have this score function, then notice this. Oops. So this is one expression I have for expected value of x given zt, right? Now, if I go back, oops. So remember, we have this expression for expected value of zt. Compare these two. Both of them are some adjustment to zt, right? And this is what we said we are going to use a neural network to learn. Compare this expression to this. You see that what you are learning is actually exactly a scaled version of the score function. So it turns out, actually, maybe there is a square root here. What you learned is exactly 1 minus square root of 1 minus alpha t times the score function. And if you think about the score function, look at what this is. This is the gradient of the log of the probability of zt, right? So what does the gradient tell you? Well, the gradient tells you the direction in which the log f of c is increasing in quickest. So here is some nice plot of the score function. So if you think about the learned score function, this is for the 3 Gaussian example. So if you take any point here, it's pointing in the direction to one of these, the centers of one of these 3 things. So you can see as you learn the score function, what you are learning is you are actually learning a vector valued function, right? For every point x, which is a 2-dimensional in this case, you are learning log, the gradient of log f of z. And they are really pointing to towards these means. So what you are really doing in sampling, you can kind of think of it as saying, I'm starting somewhere. I am going to take a step towards where the density function is high. It's almost like gradient ascent. But then it's a stochastic sampling. I'm not just going to take that step. I'm going to add a small Gaussian random variable to it so that I get some stochastic sampling to this so that I end up actually generating new samples from the distribution rather than going exactly to the same place every time. I think that's all I wanted to say. There is something we can do about inverse problems, but I think I don't want to. I think it's too much to try to do that. So I think I will stop here. The takeaway, hopefully, is this training procedure. Training and sampling procedure. Bharadwaj, can I take just 2 more minutes?
Yeah, sure. I think so. Yes.
Okay, let me show you something, another animation. So can you see my notebook?
Yes. Yeah.
Okay. So I want to just show you, it's fairly easy to write something. So, here there is a Python code where, I'm generating a mixture Gaussian data set. So this is the data set that I'm generating. So if you, oops. So I create a data set, in this case, 90,000 points. Then you define a neural network. In the 2-dimensional example, I've just defined a neural network which says, a linear layer, ReLU, a bunch of linear layers and ReLUs. It's a simple example, but if you do images, you should be careful what to put here. And then I instantiate this neural network, and key thing is this. Notice that I'm saying my loss function is a mean squared error. It's mean squared error because I care about only conditional means in the end. Right? All right. So this is the most important. These are the 5 lines I want you to focus on if you can see it. Basically, what it's saying is this. For every time, so there is a epoch. For every epoch, draw a mini batch. Randomly draw time instance from 0 to the number of steps. N steps is t. Generate epsilon. These are Gaussian random variables. Take your alpha. Generate zt. Right? Square root of alpha times x, which is the batch. plus 1 minus square root of alpha times epsilon. The input to the model is a concatenation of t and zt. Y is the output of the model. Minimize the loss function between y and epsilon t. Just call loss dot backward optimizer. It will optimize the network. So let me run the, seemed like we got disconnected. So let me run the training. So you can see I'm running the training and you should get some. Yeah, it should stop pretty soon. So then we go through a sampling step. So you can see this is the original. These are samples drawn from the original distribution. And these are samples from the generated distribution. You can say they are pretty good, right? Right. Let me actually.
You have to be careful not to overfit and so on.
Yeah, all those issues are there. You have to be careful to not overfit. Your training has to, yeah, let me try this.
So in some sense, I mean, this is not really like a plug and play thing when you learn the neural network and you have to do some coding.
Yeah, it's not really plug and, I mean, yeah, you're right. The procedure is there. It's fairly straightforward, but indeed there are tricks that you will have to use in the training itself. So, and the last thing I want to show you is this nice animation. Just 1 minute and then we'll finish. So you can see the generated distribution and the original distribution. So it's not perfect, right? So you can see some of these samples here. You can see some of these samples here. But it's a it's a pretty decent. Okay, so this is a pretty nice animation, I think. So what I'm showing here is to show that you can generate from the distribution. So I took, I think, like, I don't know, maybe 200 or 2000 points. So this is ZT, right? It's a bunch of points at ZT. Every one of them is one point. Every point here is one vector, it's one realization, right? And you can see over time, there is a little drift every time, and you can see those things start to separate out. In this case, it was that mixture Gaussian, so they kind of nicely separate out into the three modes of the distribution. I think I will stop here. How do I?
Questions?
There's one question. You have a question?
Actually, in the beginning, you mentioned that we don't use X for the reverse process learning, but we learned ZT minus 1 given ZT comma X, and then evaluated over X. So is this can you explain this?
Yeah. So let me quickly share my. Oh. So what I did was to say, okay, look, I want to compute expected value of zt minus 1 given zt, right? But I can do it in two steps. I can first compute expected value of zt minus 1 given given zt and x, and then I can average out x over it. But notice that this is during the training process. So what I'm trying to say is we have to separate the training process out from the sampling process. So during the training process, indeed, I will use my x. I will use my x to create zt, and from that, I will try to learn my epsilon, right? But notice that in the sampling process, which is the reverse, which is here, I never use x anywhere, right? We cannot really use x. We have to create new samples, right? But what I'm saying is the way to compute expected value of zt minus 1 given zt, in that process, I can use my, to learn that function, I can use my x. I will have to use x, right? Because that's the only information that we really have about any distribution to be able to learn zt minus 1 given zt. Does that make sense? But in the sampling process, we cannot use x.
Any other questions? Yeah. Come on. One more question, Krishna.
Yeah, sure.
Sir,
Yeah.
so instead of using a neural network,
Yeah.
so I know in which case we might need a more number of samples to train neural network to estimate. Can we use Gibbs sampling?
Yeah, so there are many ways to generate samples from X, right? Gibbs sampling is one way. There are many other sampling techniques that can be used to generate samples from X. But in general, I think all of these have several, I mean, they work well in some cases. They also have several limitations, right? So diffusion models have been very popular for being able to generate samples from very complicated distributions like images and audio and things like that. I think in general, I don't think Gibbs samplers based things have been effective for those problems. But yeah, I mean, there are many ways to generate samples from a distribution. Right?
All right. So thanks again, Krishna. So I think there seem to be no more questions from the audience here. So yeah, so I guess thanks again for attending, and special thanks again to Professor Krishna.
Thank you, Bharadwaj. It's a
Yeah.
exciting format. I wish the seminar very best, and I hope to see more of this on YouTube.
Yeah. All right.
Thanks,
Yeah.
Krishna.
Thank you. Yeah.
Thank you, everyone. Bye, Bharadwaj.
See you. So I'll catch up with you over email.
Sounds good. Thank you.
Yeah. Thank you.